So we all have to set up the same background?
I don't think so.
If you have a mail from
Monique?
Monique, then it's possible. Otherwise, I can share it with you as well. Yeah.
Yes, shall we start? Waar kan het nou maar zo? Yes, everybody is fine. Good afternoon, or maybe good morning. It depends where you are on this world. It's a pleasure for me to open this webinar. My name is Roelof Kruijsen. I'm board member of World Waternet, and I was involved in many Amsterdam International Water Week editions. The next Amsterdam International Water Week is scheduled in the first week of November in 2023, so 1 year ahead. And we decided as organizers to start a series of webinars to promote the Amsterdam International Water Week and to prepare for this event. So this is the first in the series. Together with NAT, an independent network organization which stimulates thermal energy out of the water cycle, energy from drinking water, wastewater, or surface water. We work together with them in the organization of this webinar. In the Netherlands, we call it aquathermie, or thermal energy from the water cycle. But if you have a better name, please let us know. The topic is very important. We have an energy crisis in Europe. The countries, especially in Western Europe, need to become independent from energy resources. They have to import a lot of energy now, and it's really important that they produce the energy local, of a local source. And next to this geopolitical issue, we have, of course, the energy transition driven by the climate change. More sustainable energy is necessary to avoid the global warming. I welcome all participants and speakers today. And we initiate this webinar because thermal energy from water can be a serious option. In Amsterdam, we made calculations, and you'll hear more about this during this webinar, that it can really make a difference. Thermal energy can warm and cool buildings. The technique is available, but who can be the initiator? Public or private or a combination? How can the governance be set up to reach a scale-up of this thermal energy? In summary, how do we ensure a system that is reliable with trust among stakeholders and customers? A system which is financially acceptable, also on the long term. That is what we want to discuss the next 1.5 hours. The goal of this webinar is to exchange knowledge, investigate research questions, and how we move from research to operation. Before we start with the first speaker, some housekeeping announcements. We will record this session and use it in the preparation of the Amsterdam International Water Week. Of course, you have the ability to ask questions if you want, and I ask you to use the chat for that. My colleague, André Strucker, will monitor the questions and will insert them sharing during this webinar, if it is possible. If you have many questions, of course, the time is limited, but we will try to answer as much questions as possible. We will have 4 presentations, and after each presentation, we take some time to answer the questions. Now ask André, do we have some questions to the audience before we start with the first speaker, or is that not the case yet?
Yes. Carla, can you bring in the poll questions, please?
So if you want to answer these questions, we get a better understanding of our audience today.
If you go to the poll button, then you see the first question. And the first question is, are you familiar with thermal energy recovery from water? And you can answer this with yes or no.
Okay, we see that a little bit less, 86% is familiar with energy recovery from water. 30% isn't. The next question.
Thank you. Carla, can you bring in the next question, please? The next question is, do you see opportunities for thermal energy recovery from water in your environment or from your field of work? You can answer this also with yes or no.
I can't see it at my screen, so maybe you can.
It's 100% at the moment that people see opportunities for thermal energy recovery from water.
Well, that's optimistic. Yes, that's good.
Well, I think we go to the last question. Carla, can people see also the last question? And the last question is, what topic are you interested in? And there's an option 1 and option 2, but I don't know what the options are. So I think we will skip this question and go to the last question. And that, let's see if this is. Do you see? No, I think these are the questions for later on in the during the session. So these are the questions, Roelof. Thank you.
Okay, thank you. You see, it's handmade. What I said, it's the first webinar in the series, so it's not all as professional as it should be, maybe. But we hope you enjoyed it, and we have a very fruitful 1.5 hours. I now like to introduce the first speaker, Henk Looyen, from the Netwerk Aquathermie. I already mentioned it as a co-organizer. Henk works with both the National Water Board Rijkswaterstaat in the Netherlands and the Network on Thermal Energy of Surface Water, Wastewater and Drinking Water, NAT. Henk translates policy ambitions into daily practice and vice versa. He aims for innovations with a sustainable future. Henk will explain the technology and will provide an overview on the state of aquathermal energy in the Netherlands. Henk, the floor is yours.
Thank you, Roelof. And I ask Carla to, yes, okay, I see my presentation. And I will try to skip to the next one. Yes, well, actually, there's not much of an introduction to be made so far. Roelof made it very clear what I do for a living now. At Rijkswaterstaat, I work 2 days a week at the Netwerk Aquathermie. I will call it aquathermal energy if it's allowed, because the full term I found it quite hard to remember. But I work with aquathermal energy for about 6 years now, so I think I can explain some of the things, and I try to make clear where we stand in the Netherlands with this sustainable source of energy. So what is aquathermal energy? Well, we use the heat from water sources, from wastewater, drinking water, and surface water. And this picture you see this focuses on the surface water, and actually, it's the point is that in the summer the sun shines into the surface water, and it warms up to about 20 degrees, sometimes even to 25 degrees Celsius. And this warmth you should actually try to be able to use it in the winter when you need it most in the built environment. And that's what we mostly do in the Netherlands. We store it in ATS systems, aquathermal energy systems storage. Okay, somebody said I cannot hear Henk. I don't know what to do about it. Anybody else with this problem?
Sorry, Henk, I can hear you very well. Maybe
Okay.
people have to put on their microphone. Is that
Okay,
the thing?
then I don't know if I can be of any help. I don't think so.
Yeah.
I'm sorry for that. Anyway, we try to store the heat during the summer and then pump it up again and use it during the winter. And there's still a possibility also with the larger surface waters, the rivers and actually the bigger surface waters, to also use the water in the winter. So without the storage, then the efficiency of the heat pump you have to use to get the level of temperature you need in the buildings is going down. So it's actually less efficient. But still, it's also possible in the bigger waters. And now that I mention the heat pumps, I think everybody knows about heat pumps nowadays. And with the water actually as an environmental source, we talk about aquathermal energy, of actually thermal energy recovery from water. And of course, there's the air and the surface. The subsoil is also a possibility to use. Then you have to add 25% extra electrical energy to get 100% heating of the built environment. So that's a possibility where the COP, the coefficient of performance of the heat pump, is 4 in this case. Mostly with when you use the air, there's the COP is less than 4. So actually, water is as a leveled level temperature. So that's actually better for the as a source for the heat pump. Well, so what's attractive about aquathermal energy? We have surface water, drinking water, and sewage water. I call it sewage water here, but it's also wastewater. And if we can, if we see it from here, then surface water is widely applicable. There's a great potential. We made the potential clear in several investigations. There's a possible improvement of the water quality or for the ecology. That's not in all cases. There's a lot of discussion about this, but some of the waters are really too warm during the summer, and that's not good for the ecology. So if you can just derive some of the heat and put the temperature a bit lower, that's actually better for the environment and for the ecology. And it's also possible to make cooling of the water of the built environment with surface water. Also with drinking water, both drinking water and sewage water are brought in pipes, and that's actually sometimes easier to derive to recover the heat from them. And with the clean water pipes, there will be no pollution in the heat exchanger you use. So that's an advantage for drinking water, especially. And the large supply pipes, which bring the I don't know how to call it in English, rough water before you actually really cleaned it so that it can be drinking water. There are large supply pipes going through the landscape, and you can use it with a great potential. Also, cooling is possible. From sewage water, the specifications are that the temperature of the sewage water is quite constant during the winter. So that's and also higher than surface water. So that's an extra advantage. Raw water, it's called. Michiel says, thank you. And if there's temperature or heat derived from the recovered from the effluent, so that's when it's okay. Then there's a gap here in my head with the English word for cleanage of the sewage water. Anyway.
Treatment.
Yeah, okay, the treatment plants. Thank you. So if you the effluent is flowing back into the surface water, and then well, if there's no heat going into the surface water is also better than if it's an extra heat into the surface water. So there's no regret for this. And then in general, by 2050, there will be no CO2 emissions because we only use electrical energy then. And in the Netherlands, everywhere there is water or pipes with drinking water or sewage water. So there's really a large potential. And as a last one, it's a good start for expandable heat network. So you can begin with this quite small one, and then it's aquathermal energy is really right to use. We made a Green Deal aquathermie, aquathermal energy, with a lot of parties. Oh, I see slide 3. Is this okay? No, it's not okay. I don't know about that. How to? Okay, I'm at 6 now. Actually, I thought.
Seems not to be automatically changing.
Oh,
so
I
if you
see.
go-
I see.
But we can do it ourselves. There is a button under the.
Yes. Okay.
So you just have to say which slide you are, and then people can click
At
it themselves.
at 6. At 6. I'm sorry. I thought I had the I had the thing
Yeah,
too.
go ahead,
Okay.
Henk.
Okay.
You
I'll
can
just
see.
go ahead. Yeah. Thanks. The Green Deal aquathermie, induced by the Dutch Climate Agreement in 2019, I think it's signed by everyone, and of course the energy transition. We really wanted to try to put all the mapping all the value and the application of the aquathermal energy in line with a lot of parties, and to really try to get joint fact finding for what are the facts and how to compare it with other sustainable sources. So this was in May 2019 we started the Green Deal, and it's now finished in May of this year, and we are now working on a progression, on a restart actually, to get them to the next phase. And this is why also the Netwerk Aquathermie not is working.
Sorry, Henk, I don't want to wrap you up, but we're running a little bit out of time. So if you can fasten a little bit.
Okay. Okay, and then I'll fasten 7, and then I had 5 specific knowledge challenges on technology, on the potential itself, and how about to fund it, how about to do the governance, which role does everybody play, which party, and of course into the environment, so the impact on the water system and the ecology. I will fasten them up really. So next one to number 8. Then the sharing of the knowledge. We wanted to share the knowledge not only within the parties involved with the Green Deal, but also everyone who gets involved with the energy transition and the heat in the built environment specifically. So we built this site. We have an inventory of the realized projects, and we put that on aquathermie.nl. Of course, on social media too, and we had communities of practice, for instance. To number 9. And then we try to broaden and deepening the network. So more parties you should have involved, and everybody should know about the investigations we had made or other parties have made. So we try to really centralize the information in total. And of course, securing this knowledge through agreements with several parties. So to the next one, to number 10. Then what we see is that there's a really rapid growth of initiatives, even more than 125 now. And well, we think that we made a sort of a forecast from NAT that we think that 200,000 households could be installed with aquathermal energy in 2030. And one of the main challenges is how do we get from research with what we've done the last 3 years to realization. And maybe it's possible to work on European cooperation. So this could be a start today. And this is actually what I wanted to present. And I see there's still a number 12, or no, this is it.
Okay, Henk, thank you very much for this interesting presentation. I looked at the chat. Is there any question to Henk at this moment? Otherwise, I have a question. It's in the Netherlands that in 2050 no natural gas can be used anymore. And what are the challenges you see? You mentioned 2030, 200,000 houses, but what about this scaling up? How do you look at that?
Well, the scaling up, I mentioned that there are several initiatives now, more than 125, and what we see is that the initiatives getting better and bigger and bigger. So what the practices now is from about the average is about 400 households in one system. Sometimes a bit bigger, but what we see now in the initiatives that it runs up to 6,000 or even 10,000 households at once, and that's really a trend. So I think it's going to be scaled up anyhow.
And is it the private sector or the public sector who is taking these
It's
initiatives?
mostly the public sector, mostly the communities of yeah, the governments, local governments, and yeah, also sometimes from bottom up, actually the inhabitants of a certain neighborhood who think, okay, we can do this collectively.
Okay, there is a question, is there a special funding for this kind of project?
There is national funding, it's not specifically for aquathermal energy, but it's also in a bigger subsidy context. But there's also some of the forms of aquathermal energy worked out in this subsidy.
And a question of Daniel, what about saltwater areas?
Well, that's really interesting. We in the Netherlands we have only one project which is using the seawater.
Yeah.
But we see now with the inventory in Europe that in Norway, in Sweden, in Wales, in Scotland, we see several projects who use the seawater. So it's definitely possible, and that's actually, yeah, it's a source without limits.
Yes, maybe Magnus from Sweden can tell a little bit more about that.
Yes.
So thank you very much for this interesting presentation, this start. Well, we have to start up, but I think and I hope that everybody can be connected, everybody can hear what is said. And I would like now to introduce the second speaker, Harry de Brouw from Waternet. He is a project developer of thermal energy projects and a member of the program team of about 15 people within Waternet, the water cycle company of Amsterdam region. He is known in the Netherlands for having developed a viewer accessible to everyone. With it, you get a few minutes and insight at district level into whether thermal energy resources can cover the heat and cold demand of the buildings, and whether further research into feasibility is interesting. This is highly appreciated by initiators at municipalities, building owners, energy cooperatives, and housing corporations. Harry was asked by residents of the Amsterdam Oostoever neighborhood to investigate the possibilities for a collective system using thermal energy from surface water as a source. He identified problems with poor water quality and the NIMBY effect, not in my backyard. What solutions did he come up with? And that's what you are going to hear now. And Harry, I'd like to give you the floor and ask you to stick a little bit to the 10 minutes. Thank you.
Yes, thank you, Ola, for the introduction. I'll try to keep it to the 10 minutes and I'll share my screen now. Okay, so my name is Harry de Brouw, and I'm working for Waternet. So it's the water cyclist organization for the metropole area of Amsterdam. We provide safe, clean and sufficient supply of water. We work for the regional public water authority, Amsterdam en Vecht, and for the municipality of Amsterdam. And well, we have about 20 thermal energy recovery projects, and I'll show you one of them as just been introduced. To start off with, I want to focus or to get your attention to some major challenges we have in the urban area. One of them is energy transition. We heat our house with natural gas, and it has to be replaced by a sustainable system. And this has a large influence on people's neighborhoods, inside their houses, and as we see now, also in their wallet. Water quality is suffering from an abundance of nutrients, often combined with a lack of flow, and that causes algae growth, especially in the hotter summers. With climate change, we see longer periods of drought and more frequent intense rainfall events. Well, biodiversity suffers from a shortage of green space and often also with the monocultures. And well, with all these problems and many more that I haven't mentioned yet, people are getting continuously challenged by those changes, and they raise their voice to object against the impact it has on their lives. So if you want to tackle these challenges, and we need to come up with integral solutions. We cannot afford to think per sector. We need to look for a more integral, sustainable way. So let's have a look at the thermal energy recovery from some surface water and how this process works. And Henk has already told you about this. And well, our goal is that we want sustainable heating of houses and buildings. And the means we have is that heat from surface water. And well, what we actually do is just pump. We pump large volumes of water through a heat exchanger. And what do we need then for that? It's pipes underneath the ground, and also a technical building where you extract heat from the flow and then pump it to all the households that need it and buildings. And this is often a challenge, since this technical building, I'll just show you a small one here, often they're even bigger, they're above ground, and space above and underground is running out. People prefer not to have a large ugly building in their back garden. The energy transition stagnates if current methods of the city development remain unchanged. So we have to deal with it in a different way that we're used to. And then the thought came up to us, and that is, what if pumping is an enabler for the integration of sustainability? What can pumping do more than just... So we continued from there, and we examined, or we researched this question. So first, we said, okay, by pumping water through a heat exchanger, you can harvest heat. But also, if you pump water, you have it already in your hands, and that gives the opportunity to maybe filter nutrients. And nutrients are often there are too many in our water system, and it causes algae growth. So let's get rid of them. We want to increase biodiversity, which can happen if you start pumping water in the ditches. Water starts moving, and that can cause water quality improvement, but also by cooling water, there are opportunities to improve the biodiversity. After heat has been recovered from surface water, what we do now in the thermal energy project is that we hide the stream. We put it in a pipe, and it returns to an open water body. But we miss an opportunity here. We might as well show the water returning over land and don't hide it underneath the ground. This gives opportunities for recreation, but also for biodiversity when you design it in a nature-friendly setting. This picture here is an example from Portland. Unfortunately, they forgot about recovering heat, but they had, well, the designer made a very nice effort, and it's, I think, a very well done project on how to show water flowing in public space. You could imagine that the structure is being the technical room with the return waters cascading down. We can also improve water management by, for example, infiltrating that returning flow of water into the ground in periods of drought, or maybe drain the ground in periods of rainfall. As Henk already said, this system is very local, and that gives opportunities to have local ownership. People can organize themselves in an energy corporation and have their own heating company with heat from the neighborhood for their own neighborhood. Well, that last thing is something that's happening right now in the neighborhood of called Oostoever, that's in Amsterdam. And well, the story I just told you, we took that along and went to the local energy corporation, and they said, okay, we have this idea and we want to challenge you with some questions. Well, this neighborhood has about 1,100 houses. It's built in the end of the last century, and it's next to a lake, a large lake, the Sloterplas, and it has water quality issues due to an overload of nutrients flowing in from the surrounding area to the lake. First thing we did is we used our online tool, the omgevingswarmtekaart, and the tool is a fast way to figure out what the heat demand is of a neighborhood, but also what the heat availability is from different heat sources in the surrounding. And this tool shows that there is enough heat available from the sewer systems, but also from the Sloterplas. Well, it's very large, so there's more than enough to heat, I think, up to 100,000 houses around there, or well, let's say 30,000 from the models, but I think it's much more. So it's more than enough for this neighborhood. So we chose this surface water body as a source for this neighborhood and continued from there. Well, we wanted to look for integral sustainable solutions. So not only extracting heat from surface water, but what other sustainable goals can we achieve? To do this, we applied a method. It's called the integral design method, and it's geared to programming public areas in an integral manner. In this method, public and private parties, they work together from an early stage. And the goal is to connect multiple opportunities to ensure that developments lead to a better social and healthy living environment. And the municipality of Amsterdam has extensive knowledge of this method and published a handbook about this. So we applied this method together with the residents of the neighborhood who are organized in the energy corporation Oosthoeve Duurzaam. And the goal was to identify problems in the neighborhood which heat recovery from surface water can help to solve. Also, we asked the residents under what conditions they would gladly have a technical room in their back garden. So, Pimby, please, in my backyard. And in the next slides, I'll show you the results from this exercise. So first, we looked at how can the building look like, a technical room, and we came up with different shapes, maybe with a street artist upon it, packed it with green walls. We also looked at the outlet, as mentioned before. You should maybe show the water instead of hiding it. So it could be a fountain, maybe a cascade, or a playground for kids, a pool. And we looked for multifunctional use of a building, not only being a technical room, but maybe it can be a play object. Maybe you should combine it with a public space utility, or for example, here it's a public toilet, or lockers for people who want to go running and store their shoes. It's next to a lake, so maybe swimming equipment. It could also be a landmark for the neighborhood as a recognition point, or maybe you want to invite people to show you how this new technology looks like, or you can make it part of in the nature. There's a park zone as well, so maybe you can make it part of that park zone. So the residents came up with all these ideas, and in the end, we focused on 3 different solutions. Possible solutions are concept ideas. Actually, I'm going to show you one of them, and that is. There are old fermentation tanks in the area. It used to be a treatment plant, and we thought that all these tanks were used. One of them is an apartment, for example. But the residents, they pointed us that one of the tanks is probably empty. It has no roof, and at first it was thought it was a storage place for water. We found out it's probably empty, and well, it's of course a very nice idea that you have an old building that's not being used. It used to have a water function, and then maybe you can use it again for the new water function. Then we found out that the ditches on the back side of the area, they have a bad water quality. That's mainly because they're not flowing. And the idea now is that you can pump water from those ditches, bring it through pipes not too far to this old fermentation tank. There harvest the energy, and then let the return water flow towards to the lake and make it visible. How, we don't know yet, but make it attractive to the neighborhood. And then before the water enters the lake, have a reed bed filter to filter the nutrients. This is the basic idea we have right now, and this has to be further researched in a feasibility study, and of course, get more people from the neighborhood involved so they can speak up and think about this idea. And well, the getaway I want to give you is this old verb from Steve Jobs saying is that you've got to start with the customer experience and work back towards technology and not the other way around. And this is for what Apple did for their ideas, and I think we also have to apply this for our field of work. Thank you.
Thank you very much, Harry. It's a very nice statement you made at the end. Let the customer be first. There are a few questions. Is the ambient heat map usable at EU level?
I wish that would be true. We put a lot of effort in there to make it usable for our own area. Other water boards or water organizations are starting using them as well. There's another map. I think Henk already told us about that's used for a national level. I think any country or area that really wants to push this technology forward needs a map like that to make it visible and accessible. So it's easier for parties to hop on and exploit this technology.
Okay, thank you. And another question from Michiel. And does it take into account existing systems in thermal, in outflow of those?
The map I just showed, or
Yes.
Yeah. So for example, the high temperature district heating system is also in there. So any source of heating is included in the map.
And there was a last question. Do you need a water cycle company for this, or can a drinking water company or a wastewater company do the same?
Yeah, the governance is a good question, and this is something we still have to find out ourselves. The thing I'm seeing at the moment is that Waternet works for both the municipality of Amsterdam, and that's the party that needs to get 1 million houses off natural gas. We work for them, so that's the demand side, and we also work for the water board, so the water company Amsterdam en Vecht, and they have all the energy and offer. So bringing those two groups together, demand and offer, we are right in the middle of that. So I think it's logical for us to play an important job in there.
Okay, Michiel is coming back in the chat. I mean that these reduce the capacity for aquathermal systems of water bodies. Is that taken into account?
Sorry, say again?
I mean that this reduce the capacity for aquathermal systems of water bodies. Is that taken into account?
Yes, what it does, it looks at the flows in the system, and then we research how much energy can be harvested from that.
Okay,
Yeah.
Thank you. Thank you very much, Harry, for this this beautiful example working together with the inhabitants in this area. Thank you. I now like to turn to the next speaker, Magnus Arnell. Magnus is a researcher at the Lund University, the Research Institutes of Sweden. Magnus will describe a model-based citywide assessment of the impacts of upstream wastewater heat recovery on the sewer system and the wastewater treatment plant, and comparing wastewater heat recovery in different positions and to a varying extent. So please, Magnus, may I give you the floor and ask you to look at the time for 10 minutes. Thank you.
Thank you very much for the kind introduction and for inviting me to come here and present to you. I hope you can see and hear me and see my slides. Excellent. So I will focus primarily on heat recovery from wastewater. And you were asking for a term, and the one that we have been using is wastewater heat recovery. So in short, WWHR, that I will also use in this presentation. So if you look at the urban water cycle from extraction of raw water, production of drinking water, distribution, using it in households, collection of wastewater, and treating it before discharging it back to nature, 10% of the national energy use typically goes into the urban water cycle, and 90% out of that is used for heating of tap water by customers. That means that there's a large energy potential being practically wasted today. And it is possible to recover this energy. It could be done in household appliances, primarily showers, but also washing machines, etc. It could be done from on building scale, on the exit wastewater from buildings. And doing it very much upstream has a higher temperature. On the other hand, a low and quite variable flow, making it more feasible typically to do it with heat exchangers rather than heat pumps. Then we can also do it in wastewater sewers, and in the end at the effluent of the wastewater treatment plant. And doing it down closer to a treatment plant or in the sewers, the main sewers, some of the energy is lost to the ground surrounding the sewers. But on the other hand, the flows are higher and typically more stable. And that means that we can do it with heat pumps. Another important difference is that if you do it on property level, typically the property owners get the benefits from the heat recovery, while doing it downstream, it's more of a collective benefit for the utility or the utility customers. So is there then a risk with doing heat recovery in wastewater? And now I will be talking from very much of a Swedish perspective, saying that Sweden is a cold country. We have a cold climate, and that means that the wastewater, the raw water, is typically quite cold during winters. And the wastewater treatment plant biological treatment processes sort of rely on the heat that is also added via the hot tap water. And recovering some of that heat upstream the wastewater treatment plant provides a risk for a lower influent temperature and thereby impacting the performance of the wastewater treatment plant. And before we started our project, there was a problem that no one had really done that analysis on a system level. If you are recovering heat upstream, how much would actually the influent temperature at the treatment plant being reduced? So we set up a quite large research project, national research project in Sweden between Lund University and the Research Institutes of Sweden, with 3 different water utilities involved. And this was funded by a national research funding agency, Formas. So to do this system-wide analysis, we developed a model tool. So both for the wastewater from households, flow, temperature, and composition. The wastewater heat recovery equipment was modeled, the energy balance in the sewer network, and also the performance and energy balance of the wastewater treatment plant. And then we connected all of this to do a system-wide study. And we had 3 case studies in our project. It was the city of Malmö, where we modeled a large part of the urban catchment. We had the wastewater utility Käppala in northeast part of Stockholm area, which has a large tunnel system that was modeled, including their treatment plant. And then we have the city of Linköping, which is the 5th largest city in Sweden, where we modeled the whole catchment area and the treatment plant. And I will focus now on the case study from Linköping. So the wastewater flow to the treatment plant is 42,000 cubic meters daily. That corresponds to about 180,000 person equivalents. So we modeled the whole sewer catchment area in subsystems, and we connected that to a calibrated wastewater treatment plant model. And this we done by combining all of the subparts that we developed in the project. We simulated 2 periods, one in January and one in April 2020. And onto this, we added a quite extensive uncertainty analysis where we varied sensitive parameters in the models. It is interesting to just say something about the treatment plant. It's in the main line a quite traditional wastewater treatment plant with an activated sludge treatment at first with intermittent aeration, but then they also have a post denitrification process on an MBBR process, moving bed biofilm reactors, which I will come back to impacts the results. So then we had the whole catchment, the whole city, the whole treatment plant, but then we implemented in the model scenarios where we tried the 4 different positions where you could implement wastewater treatment heat recovery, but also different degrees. So the 16% of the wastewater, 42% of the total wastewater, or 77% of the total wastewater. and compared that to the default scenario with no heat recovery. Looking just briefly first at the results for total flow and influent temperature, we can see that we model the flow quite accurately. The data for temperature is substantially smoother than the model provides, but the average for the model is very close to the average of the data. So for the results then, first, energy recovery. So the maximum heat recovery in all of our scenarios was in position 1, so that's heat recovery at showers in buildings. There we could recover on average 120 to 330 kilowatt hours per person and year. More energy could only be recovered if we were doing it with heat pumps in main parts of the sewer systems during summer. During it at the effluent of the houses, position 2, provided some 95 to 185 kilowatt hours per person and year. It's also interesting to note that it's not only the recovered energy that's of benefit for the property owners, but also the reduced peak power demand. That means that most property owners have some kind of power tariff on their heat from district heating or on electrical power, meaning that their peak power demand over a year or over a month or some period sets their fixed tariff rate. And by reducing that maximum power demand, they can also not only save on the kilowatt hours, but also on the fixed rate of their power or heat. The temperature at the influent to the treatment plant was reduced with a maximum of 1 degree compared to the default case, and that was when the heat was recovered in position 1 and with the maximum rate of implementation. And we were surprised that this was actually quite limited impact. So the effluent from the buildings is of course larger, up to almost 6 degrees reduction, but then that's narrowed down, and when it comes to the treatment plant, it's only a 1 degree reduction left. If we did heat recovery in position 3 with heat pumps, so in the sewers on the large part of the wastewater, we could get up to 2.5 degrees reduction. How does this impact the wastewater treatment plant then? Then we have primarily been looking at the nitrogen, the biological nitrogen removal at the plant. And it's actually a very, very small impact on the nitrification and the total nitrogen removal at the plant. It's almost insignificant differences between the different cases, as you can see in the figure here. And there is no risk that the plant would exceed the effluent limits as an impact or as a consequence of the heat recovery. We did also enforce larger temperature reduction up to 3 degrees, which, just remind you, we couldn't simulate that in the catchment, but if that would happen anyway for some reason, we couldn't see any large impacts on the total nitrogen removal in that case either. Slightly higher, but not dangerously high. And this was actually true for all the 3 case studies and for all the different scenarios. So this tells us that these results are quite robust. So just some other details. As I said, the ammonia reduction that we were looking at just recently was for the total effluent of the plant, but they have separate different nitrogen removal processes at the plant. So one could wonder, how would it be at the secondary settler effluent? And there the increase is slightly larger, as you see at the most left picture here, but still not in a rate or a level where it would risk any effluent constraints. The alteration in temperature also impacts the aeration energy and also the carbon addition at the plant. And this would be quite specific for any treatment plant. So that would have to be evaluated from case by case. So coming to my conclusions, we can see that for the effluent of the building, wastewater heat recovery can lower the temperature from up to 5.5 degrees Celsius. At the same time, that only means up to 1 degree Celsius heat reduction at the wastewater treatment plant influent. If we are not doing heat recovery with heat pumps in the sewers at a large part of the wastewater, then we can have higher reductions. And in general, upstream heat recovery did not have any impact on or major or significant impact on the nitrogen removal at the wastewater treatment plant. And it depends on where we implement it also. So yeah, I think that was my main take-home message. It should also be there is one consideration, of course, and that is that even if we are not seeing an impact on the effluent limits today on the treatment plant, it might mean that the total capacity of the plant might be reduced. So by lowering the temperature, even if we don't violate the effluent constraints today, if they have an increasing load prognosis or load forecast for the upcoming decades, it might mean that they hit that upper level at a few years earlier time ahead.
Okay, thank you, Magnus. It's very interesting to see how you did this research on the nitrification capacity of the treatment plants. We are a little bit running out of time, so you see there are some questions. I will take only a few out of it. Can you say a little bit about the costs of the different scenarios?
We did not investigate the cost in such a way that we calculated the cost for installing heat exchangers in the different positions. No. We did calculate only the energy recovery in terms of kilowatt hours. That could, of course, be converted to euros or similar, but no, we did not do the cost calculations in any more.
What was the effect of the soil temperature in which the pipes are? Is there?
Yeah, that's one of the most influential parameters or variables in the model. We did model the soil temperature, so we have a varying soil temperature over seasons in our model, and that's a very influential parameter, yes.
Okay, thank you. Well, there are some other questions, but unfortunately, due to time, I think maybe we can answer them later. I'd now like to go to the last speaker. It's Jawara Ahmad. Jawara was born in Pakistan. She's also a young water professional. She was born in 1986 in the capital Islamabad. She obtained her bachelor and master degrees in environmental sciences. In 2015, she joined the Technical University of Delft as a PhD student, where she focused on resource recovery, thermal energy, cold energy from drinking water distribution systems, without affecting the water quality. Her ambition is to integrate the idea of resource recovery from drinking water on a larger scale for application of sustainable cities and circular economies. This is to meet the UN Sustainable Development Goals 6, 7, and 11. Jawara, please, the floor is yours.
Hi, good afternoon, everyone. Let me share the screen first. Yeah. Do you see my presentation? Is it visible now?
It was visible. Now it's not visible. Now we see your screen of TU Delft.
Yeah. Is it visible now?
Yeah,
Yes,
it's clear.
yes.
Yeah.
Okay, good afternoon, everyone. I'm Javeria Imtiaz Ahmad. I recently finished my PhD. I'm going to graduate in December, on 14th of December. And it is very nice that I hear the story of surface recovery of thermal energy from surface water and then wastewater. And now we are moving to the third part of the urban water cycle, that is drinking water. And if we recover thermal energy from drinking water, what are the effects on microbial water quality? So we are covering the whole urban water cycle. If I talk about drinking water distribution systems, it means that drinking water in Netherlands, I'm specifically talking about the Netherlands where we drink water without any disinfectant added. So it's microbially safe and stable drinking water. And in the Netherlands, we have around 120,000 kilometer long distribution networks, and every year 10 drinking water distribution companies distribute around 1,160 million cubic meter water. So that is a lot of water for 1.7 million of population. So, but there is also a source of energy recovery. There is a potential of both coal and heat. So first we look at the coal recovery because there we see more potential because most part of the years the drinking water temperature remains below 20 degrees in the Netherlands. And here you can see the window of opportunity where we can recover coal from the drinking water, because according to the Dutch drinking water regulations, the temperature of the drinking water should not be higher than 25 degrees within the distribution networks. So we have this window where we can increase the temperature of the drinking water after recovering the coal from it as thermal energy, and then not going beyond 25 degrees. And why we want to recover coal? Because there is more opportunity, and also because of the extreme ambient temperatures. As we see the warm summer this year, like hot summer, that means that there are increasing the cooling requirements. And there was a case study where they said that the cooling requirements only for the non-residential buildings in Amsterdam is around 2,161 terajoule per year. And the cooling potential from the drinking water distribution systems of Amsterdam is around 2,800 terajoule per year. So we see a lot of opportunity for coal recovery in the Amsterdam and overall in the Netherlands. And now the point came that, okay, we recover coal during the winter, and then actually the need for the coal is in summer. So we have Aquathermie thermal energy storage system, which are and for other energy sinks, and those can be utilized for saving the coal winter and to be utilized in the upcoming summers. And it will help, of course, in reducing the carbon footprint. So we have an opportunity to recover the coal. The coal is available in the form of drinking water, and we have technology available, heat exchangers, and aquathermal energy storage system. So what is the challenge? The challenge is that we will increase the drinking water temperature, but how it will affect the microbial water quality, because especially for the distribution networks in the Netherlands and few other countries where we distribute water without disinfectant, then how we are going to maintain the microbial water quality when the temperature is being increased. And sustainable energy is a good thing, but we don't want to compromise the drinking water quality, because that's the prime aim of the water utilities, to provide safe. There were some knowledge gaps that we started 5 years ago to answer. So water quality, not only in the drinking water phase, but also the biofilm. That's the small thin layer that is made in the that is being made inside the walls of the pipe. And yeah, for the people without background of microbiology, you can see the biofilm when you put water in your glass, and it will stay there for a few days. When you empty it, then there is a slime layer that's called the biofilm. And then we see that what is the maximum temperature? Shall we go up to 25 degrees or maybe beyond? Then we have more window. and the temperature difference, because if it's 4 degrees and we go to 25 degrees, there is a difference of 21 degrees. That will also make some difference when we talk about in terms of opportunistic pathogens, because they have some special window to grow after the temperature is being increased. And then the last part of this research was heat exchanger location. Shall we place it on service lines like the heat exchanger to recover the water? And then even people can get water, warm water at home. And then they, in the winter, they have to utilize less energy to warm up their water. We have to put it in the reservoir, like the big water pipes before the reservoir. So it will have less impact in the house. So there were some questions. We started with the pilot study at EU Delft with 3 distribution networks, one with cold recovery, where we set up the max temperature of 25 degrees. One where we put non-operational heat exchangers, but just to see like it's an extra material and it's a drinking water. So we really want to be very careful. And the third system was the so the results, this is ATP. This is one of the methods that measure the biomass within the drinking water phase. And then with this one, we check both after cold recovery system, after non-operational heat exchanger and reference system, and the dotted line is the temperature. We did it from May 2016 to January 2018, this research, and then we saw that actually there was less differences between systems. And if we, I'm not going deep into the analysis behind this or the experiments, but this is about the microbial community composition. So there are not only one or 2 type of microbes, but hundreds of type of microbes that we looked into it through gene sequencing. And then we see that the clusters of the water samples from the 4 locations, that is feed water, after cold recovery, after non-operational heat exchanger, and the reference system, clustered together based on the months, not based on their location. So the take home is that it's because of the sudden increase in temperature, there were not much differences, but we see more differences because of the seasonal changes in the feed water microbial community. And keep into account that this water that we used came from a treatment plant that took the water from the surface water. So there we have more effects of the seasonal temperature change rather than the water that we take from, let's say, from the North Holland, where we use downs to treat the water. And then we went into the biofilm formation from 7 days in the reference and control system till 700 days. And then we see that biofilms within unchlorinated systems get stable after 84 days. So we don't see any changes after 84 days in terms of microbial community composition, but the biomass was changing. And then in the after cold recovery system, we also see that the biofilm even gets stable earlier compared to the reference and control system. Where the temperature was more fluctuating compared to the cold recovery system, where temperature was set at 25 degrees for 700 days. So that was also kind of a good news for us. And then opportunistic pathogens, those were more critical in terms of temperature changes. So I'm only showing the Legionella, which is more, which get more of our attention. And then here is like the number of samples that we measured from. And that if the Legionella is present in the feed water, then it definitely gets.
Everybody wants to put to mute his microphone because we have some noise.
And then after cold recovery, of course, it will increase. But if they are not present, then there is no chance that they will regrow after the cold recovery system. So then we are safe from drinking water perspective, from biofilm recovery, biofilm growth perspective. Now, what should be the Tmax? Shall we go till 25 degrees or shall we go to 30 degrees even to get more cold recovered out of the system? Then we did another study. And then in the drinking water phase, we don't see any changes. 5 and 30 degrees and our reference system, because in that water opportunistic pathogens were not present, so and not detected, so they were not increased after cold recovery. And traced the biofilm for 224 days, and then there was less biomass in cold recovery system compared to 25 degrees and reference system. That also was a kind of another authentication, because we already did it for another water in an experiment, and there we also see that the biofilm after cold recovery gets stable earlier, and the same has been seen here. And then opportunistic pathogens were not present in the feed water. That means they were not present in the biofilm, because the biofilm take everything, all the microbial communities from the feed water, from the drinking water, and that grows inside the biofilm. So feed water gets stable over time. It was a more stable feed water as compared to our first experiment, because here we don't see much seasonal temperature differences, because water go into the downs after getting and then getting treated. So there were less seasonal differences. And then comes another question that, okay, you go up till 30 degrees, up to 25 degrees. Then what if people complain, oh, we don't want hot water at our taps? Then we did some modeling study, and we see that almost after 1 kilometer of the heat exchanger, the water goes back to the temperature that was before the heat exchanger. So then we don't have any problem with the location. Then it's known that 1 kilometer distance is kind of a roadmap that we can take, that we should not place the heat exchangers within the distance of 1 kilometer from the service lines, let's say. And if we go from 25 degrees to 30 degrees, there is more potential of cold recovery. This is one of the full-scale system that starts its operation in 2017 while we were doing this study, and they take it's a Waternet, the water supply company of the Amsterdam, collaborated with Sanquin. They need cold during the winter as well. That's why the cold supply throughout the year. And the blood bank took heat from the drinking water, cold from the drinking water from the big pipe. It was a big pipe coming from the transport line. And then they took 15 degrees. And I think this year or the last year after our results, they went a bit higher, around 17 or 17.5 degrees, because it's safe. It's safe to operate in this. So the key facts are that cold can be recovered. It's microbially stable. At our research in 25 and 30 degrees, we see no changes in terms of opportunistic pathogens, but it always depends on the feed water quality. If it's true for the water networks that we studied, but maybe for another water, drinking water, it's not true. The microbial community composition is different. So a baseline study is very important. And then in terms of biofilm, it reaches to its stable stage earlier compared to the systems. And of course, when we go higher temperatures, if there is a question that the water can be hot at the tap, it's not true, because it go back, because it's mostly depends on the soil. The water temperature is usually in the pipes is similar as the temperature of the soil. So if it's in a big city like Rotterdam and Amsterdam, then you have to study it differently within the cities. So these are some glimpses of our experiments in Delft, in Leiden, in Waternet, and these are some analyses that we use for both drinking water and biofilms. And I'm a good proponent of thermal energy recovery, but I really don't want to compromise the water quality, so it should be in a very balanced stage. Yeah.
Thank you very much, Jawara, for this very interesting overview of thermal energy from drinking water.
Yeah, thank you so much.
I look if there is a question. Henk has a question. I don't know if I understand it well. If the growth of biofilm stops on the side of the pipe, is there also a stable situation in the water itself?
Yes, indeed, because what we prescribe, not what we suggested is that the first 2 to 3 months of operation of the cold recovery systems within distribution network, you have to be very careful because there happens more changes. And it's even true for the new distribution networks, like without cold recovery, there you have to be very careful in the first 2-3 months of operation, because then the biofilm grow, the new microbes are there, Legionella can come in if it's present in the feed water. We cannot say that there are less changes in the in the drinking water when the biofilm gets stable, but there will be less impacts from the biofilm into the drinking water phase. But if the drinking water has other kind of impacts from treatment, then yeah, then it's another story.
Yeah. Okay, a last question from Nikki. Did you consider dosing opportunistic pathogens?
Yeah, this is our recommendations for the further research, that we should dose different opportunistic pathogens at different temperatures to study it.
Okay, thank you very much for this interesting presentation. We're now coming to the last part of our webinar. We have 3 people who like to comment on what they hear. I introduce them shortly. It's Andreas Moerman. He is researcher at KWR, the research institute from the Dutch drinking water companies. After him, I will ask a question to Jan-Peter van der Hoek, professor at Delft University. And then to Dieter Staat. He is working in Brussels, and he is representing the Dutch drinking water companies and the Dutch water boards there. But starting with you, Andreas, what opportunities do you see for knowledge exchanges?
Thank you. I hope you heard me well.
Yes.
Just
now,
a small point. My children are coming from school, so if there's any noise, you know what's wrong. Yeah, I really like the initiative of Waternet to organize these kind of sessions, because I think there's a lot of opportunity to share these knowledge, just also over the boundaries to other countries. And I'm personally very interested in what's happening around Europe in this field, because it's a quite new field. I think on the one hand, on the other, we see also projects in Netherlands which already exist for more than 10-20 years. So it's, on the other hand, it's not really new, but nowadays there is a really push for more of these kind of projects. Yeah, just some observations from my side. I think we are currently still really focusing on the technical part, and I also see the need and the demand for that. We've also at KBR we have a new project proposal, which I expect to start at 1st of January 2023. We're also focusing on further research on technical issues, but on the other hand, yeah, what we're doing here is actually we can make a connection between different infrastructures. So what we're doing at thermal recovery from water, thermal energy recovery, is that we are really doing chain integration, I would call it in the Netherlands, and that's I guess something new, and that means also that we have to think about what the side effects can be of that. So we have to think about also robust design. And I will give you just one example. If we make a connection between a drinking water infrastructure and supplying heat or cold to a building, there should always be some kind of buffer between that, because if you have a failure at that drinking water site, you do not want directly influencing all the systems, and it also works the other way around. So technical, we have to think about how do we design these kind of systems robustly, but also in an organizational way, we have to think about robust design. So nowadays, I'm talking a bit from my perspective from drinking water side, but I see that we have 10 to 15 projects existing in the Netherlands nowadays. Also quite big installations, but still, yeah, it counts up to some installations per drinking water company, and that means that these projects are not currently in such a mature phase that we have implemented it completely in our daily business. And that's something that's a step. And I know that, for example, Waternet is thinking about that. How can we implement these kind of systems, this kind of chain integration completely within the daily business of our asset management, for example. So our asset managers have to know what's also the OPEX and the maintenance of these systems, and when do we have to replace spare parts, for example. So that's yeah, something I see from my side, and I think that's also something for the future.
Yes, it's very good that you mention the risks and the confidence of the customers in these kind of systems is of course very important. I thank you for your comment. I'd like to go to Jan-Peter van der Hoek for his comment, and maybe you can focus a little bit on which research questions you see, which are the unknown things at this moment.
Yeah, thank you. Well, in fact, I see 3 questions or 3 topics, and they were partly addressed in all the presentations. And the first relates to the secondary effects. I call it the secondary effects. We approach it from the side of energy, but in fact, we're all water utilities. Water is our core business. So do we know enough about the secondary effects? And they were addressed. That's good to see. With drinking water, Jawahra pointed at the side effect. Okay, higher temperature. What about the microbiological quality? And it's important because we want to supply safe water. And then the surface water, that was addressed by Harry de Brouw. Well, we can change the temperature of the surface water, but what about the ecology? As water authorities, we are also responsible for the good surface water quality. Look at the Water Framework Directive. Change of temperature can change the habitat of a system. So we really need knowledge about the effect of temperature induced by thermal energy recovery from surface water on the surface water. And the third part was nicely addressed by Magnus. He spoke about wastewater. Okay, we can recover cold from the wastewater, but the temperature goes down. How to balance the energy efficiency and the treatment efficiency? If the temperature goes down, the efficiency of a treatment plant can go down. So that's the first research question I see. The second research question has to do with the demand and supply. I think we all know there is a spatially and temporally difference between demand and supply, because in the winter we can recover cold, but we need it in the summer. In the summer we can recover heat, but we need it in the winter. Well, we use ATIS systems, but we all know there are in fact too many ATIS systems. There's interference. So the research question is, how can we find good energy storage systems to balance the spatially and temporally different supply and demand? And the third, well, I come back to your introduction. You said aquathermal energy recovery is part of the energy transition, and the energy transition is driven by climate change. But with climate change, we see a rising temperature. So then you can question, do we really need heat? No, we need cold. So with a rising temperature, we can recover more and more heat from the water, but in fact we need cold in the future, especially in the urban environment, for cooling and buildings. So my research question is, or my question is, how sustainable, how feasible is this technology, this approach, when you take into account the climate scenarios? So that I see as 3 questions we should focus on to make it even more better.
Thank you, Jan-Peter, for this overview and your reaction to the speakers. You're quite right. Global warming means we need more cold. So it's very good that you stated this item too. I switch to the last observer. It's Dieter Staat, and what I said, you working in Brussels for the Dutch drinking water sector. But from an EU perspective, will a network good? How is the EU? Is it on the EU agenda because of the political situation in Russia, Ukraine. So can you reflect and say a little bit about that?
Yeah, thank you. I represent the Dutch water authorities and the Dutch drinking water companies in Brussels, and I'm active in several umbrella organizations, and I engage with the European Commission and the policymakers over there. And indeed, the European Green Deal agenda from the European Commission and also the war in Ukraine are really pushing for reducing our greenhouse gas emissions and changing to renewable energy sources. So this new way of creating energy is really an interesting one to further develop. I know that my colleagues in up north in Scandinavia, they're already for a while really working on this, and big projects are happening in Sweden and also in Finland, where they use it for district heating. So, but they also have a different situation, a starting point than we have in the Netherlands. So the potential of this energy source are also differing everywhere in Europe. It's good to look for existing networks, because I think there are already umbrella organizations that have this item on the agenda. But it's also good to see what projects are already happening and which countries are the front runners. So I see potential, and I think it would be good to also invest in setting up a network with other companies, countries in Europe to further put this on the higher on the European agenda, but also to exchange solutions and innovative approaches, and also to make sure that if there is further research, that the broader picture is taken into account.
Thank you very much, Dieter. I think that's a very good conclusion, and you also get a compliment for that. This brings us to the end of this webinar. It's 1.5 minutes ahead for 3 o'clock. So thank you all for all these contributions which you brought to this audience. The technique is available. We really heard about that. We also see that the effects are taken into account, the effects on the drinking water quality, on surface water quality, on the wastewater treatment process itself. We are looking for the risks, but the governance is still something I think we should focus on. On the other hand, there are a lot of projects, there are a lot of initiatives. So if they are successful and if the customer know that they can have heat and cold 24 hours a day, and they're going to believe in it, and showing the good examples will help this technology further. I thank you all for this joining this webinar. And of course, I'd like to see you all in Amsterdam from the 6th till 9 November 2023 at the Amsterdam International Water Week. So put it in your agenda, and I hope that 1 year ahead from now, we know more about this very interesting topic. So thank you very much.
Thank you. Bye-bye.
Thank you too.
Bye-bye.